Hello, Algebra 2 students, and welcome to Lesson 3.6, where you're going to learn theorems about roots of polynomial equations. So in this first example, we're going to identify possible rational solutions, okay, or possible rational zeros, or you can use the different words meaning the same thing, right? Roots, here we go. We've got all three of them here. Roots, solutions, zeros, x-intercepts, all mean the same thing. Now that word rational, if you look at the first 5 letters, you see the word ratio, right? So rational solutions are the solutions that are real numbers that can be written as a ratio. Here's another key word, possible. Okay, so we're looking for possible solutions. So it appears that 4 is a 0. And then we're being asked, without substituting, how can we determine if 4 is a possible solution? So you might be thinking division, which is good. We did that in the last section, right? So I have the division started here. And then look what happens. As I do the division, I'm not going to get remainder 0. Right, that 4 times 4 gives me 16. This graph, you can see how the y scale is so blown up, right? It actually is not, it's very, very close to 4. If you go to Desmos and enter this function, you'll see, if you click on the x-intercept, it's very close to 4, but it's not exactly 4, okay? But 4 actually is a possible 0. So what do we mean by that? Well, this is one of the theorems that you're going to learn, where we can determine the possible zeros by looking at the constant and the leading coefficient. We're going to look at the factors of these numbers and set them up as a ratio. So I included some examples that we did in the last section. If you look at most of our problems, the coefficient of the leading term was either a 1 or a -1. So if we look at the constants, or our solutions, we had 1 and 6, which are both factors of -30. And the factors can be positive or negative. For this example, our constant is -22. Our solutions were 1 and 11, both factors of -22. So this is not coincidence. This is what the theorem actually states. In the next example, we got this one down to where the constant was a -6. Our solutions ended up being 2 and -3. And then for this last one, our constant was a 2. We got a -1, but still always factors of the constant. So here's the theorem. The rational root theorem says, let p of x equal all of this. This is the standard form of a polynomial, where a sub n minus 1 are all coefficients, right, down to a sub 1, and then a sub 0 is our constant. We have x to the n. This should be decreasing order. That should be an n minus 1. That's an error there. Okay, so all of the exponents are in terms of n. So what we're focusing on is, again, the constant and the leading coefficient and the factors of those numbers. So if the polynomial p of x equal to 0 has any rational roots, then each rational root has this form. Okay, so I'm going to highlight this. It's the form p over q, where p is a factor of the constant. And q is a factor of the leading coefficient. So that's why in the examples I was just showing you, our leading coefficients were always 1s or -1s. We could disregard it. But if we have something other than a 1, then we have to look at the factors of the constant over the factors of the leading coefficient. So let's take a look at example 2. Here we have a storage company that's designing a new storage unit based on the dimensions shown. The volume of the container is modeled by this polynomial, where x is the width in feet. What are the dimensions of the container in feet if the volume of the unit is 154 cubic feet? So notice in the picture they give us the height, right, 2x minus 3, the depth, x minus 2, and there's x, which is the width. Now, if the volume is 154, we're going to set this function equal to it, which makes the constant negative 154, right, because we would move that constant over. So to figure out the possible solutions here, again, these are possible, it would be all of the factors of negative 154, and again, they can be positive or negative, over the factors of the leading coefficient, which in this case is a positive 2. I don't know why there's a negative there. That should be a positive 2. Doesn't really matter because the factors can be positive or negative. So if we set up all of the possibilities, we would have all of these numbers over 1, and then we would have all of these numbers over 2. So possible zeros would be all of these numbers that you see in this orange or reddish color over and including plus or minus a half, right? 2 over 2 is 1. We would also have plus or minus 7 halves, plus or minus 11 halves. 14 over 2 is 7, which we already have. We don't need that. 22 over 2 is 11. We already have that. We have 77 over 2 plus or minus. So there's all of the possible rational solutions. Okay? And that would be a lot of testing. So we're just going to get right to it. Just so you can see the process here. It turns out that when we divide, because now what we do to test which one actually is a solution, we would start doing our synthetic division. Okay, that's a lot of possibilities though. So I've narrowed it down. 11 over 2 works, right? And I know that because when I do the synthetic division, I get remainder 0. So once I know that, remember we have the rest down to a quadratic, but we don't even need that. This is what x equals, and that's what I need. X is the width, right, of the shed. And then using the other expressions, we can plug that 11 over 2 or 5.5 into those expressions and get the other solutions of 3.5 and 8. So there's the 3 dimensions of that storage unit. Okay, the fundamental theorem of algebra. What this one says is that if p of x is a polynomial of degree n, which is greater than or equal to 1, then p of x has exactly n solutions, which we've talked about in the past, right? We've said if you have a 4th degree polynomial, it has 4 solutions. Now that's 4 solutions in the complex set. So some may be imaginary, some may be real. So if p of x has any factor of multiplicity m, then count the solution associated with that factor m times. So for example, if the equation x minus 3, quantity to the 4th power, equal to 0, it has 4 solutions. All 4 solutions are equal to 3. And this is what I was talking about the other day, last week. That multiplicity being 4, we also call this a repeated 0, right? 3 is repeated 4 times. Okay. If you looked at the graph of this, what would you expect to see? Hopefully you set a turning point, right? Because it's an even multiplicity, which means at x equal to 3, the graph would have a turning point. Okay, so knowing this, let's try finding all of the complex roots. So when you see all complex roots, that means the real roots and the imaginary roots. Okay, so what are all the complex roots of this polynomial? So our constant is -2, leading coefficient is 3. So here's all the possibilities. We could have, we're taking again those factors of 2, which are plus or minus 1 and plus or minus 2, and we're putting them over the factors of 3, which are plus or minus 1 and plus or minus 3. So I have 1 over 1, right there, 2 over 1, 1 over 3, and 2 over 3. So there's the 8 possibilities. So what do I do now? I start dividing, right? I start testing these solutions. Now keep in mind from our remainder theorem, remember our remainder theorem says that if P of A is equal to 0, right, then we know that A is a factor. P of A equaling 0 means that when I plug that in, I'm getting 0 as a result. It also means that if I did division by A, I would get 0 as a remainder. Remember that? So here's a quick little tip. You can always, for 1 and -1, often what I'll do real quick is just check to see if they work by plugging in, because they're easy to check. If 1 works, let me show you what I mean, then that means if I did 3 plus 4 plus 2 minus 1 minus 2, if that gives me 0, so let's see what I have here. 2 minus 2, nope, I got 7 minus 1, doesn't work. If I try -1, let me take that out. If I'm plugging in -1 for x, then that would stay positive. This becomes negative. Positive, negative. No, I'm sorry, positive because it's a minus and negative. And then negative. So again, I've got 2 minus 2, and this time I've got 4 minus 4, so this works. So I know -1 is a 0. Now, that's not something you have to do. You could just start doing your division if you prefer to do that, but it's sometimes very easy to test 1 and -1. I wouldn't do it with any other numbers, okay? So I'm going to list out my coefficients. At least now I know I should get remainder 0, okay? And check to see we're not missing any terms, so we're good with that. So I bring down the 3, -3, 1, -1, 1, -1, -2, 2. Okay, good. But the problem is, this was 4th degree, so now I'm down to a cube, right? So I need to keep going here. So the next thing I'm going to check is, let's see, we did 1 and -1. Let's try a 3rd. Okay. Well, actually, maybe let's try 2. I usually like trying the positives. Whoops. A little too long. Okay, so if I check 2, I get 6, 7, 14. This isn't looking good. As soon as I see I'm not going to get remainder 0, I can stop that division. Okay? All right, let's come up here. So next, let's see. We could try -2. I'm just going to try a 3rd. I'm going to stick with the positives. Okay, so if I start with a 3rd, and again, I'm going back to this quotient here, right? That's my cube. I want to bring that down to a quadratic. So don't go back to the original, or you'll never get it down to a quadratic. Okay, so a 3rd of 3 is 1. 2, a 3rd of 2 is 2/3. That gives me 2/3, and 3/3 is 5/3. Nope, that's not going to work. Okay, let's just stick with the positives. It's good to keep some kind of order. And if this doesn't work, then we have to try the negatives. Okay, 2/3 of 3 is a 1. I mean, a 2. 2/3 of 3 is 2. Add them up. 2/3 of 3 is 2. Add them up. And 2/3 of 3 is 2. All right, good. Okay, this is really good because now we've found 2 zeros. 2/3 is a 0, and -1 is a 0. And the last two we can get by solving this quadratic. All of these are divisible by 3, so I can take that 3 out, make my number smaller, and then I'm going to use quadratic formula. So it's (b plus or minus the square root of b squared minus 4ac all over 2a. So that's (1 plus or minus). That's the square root of (3), right? I've got 1 minus 4. So the I comes out, the 3 stays under the root, and there's my 2 imaginary solutions. So this process is the same as before. Right? The difference here is now we're using our rational root theorem to determine what are the possible zeros and doing our synthetic division to get it down to a quadratic, which I can then solve. So there's my 4 solutions, (1), I should include them here, and 2/3. There's all 4 solutions for x. Okay, we have an additional example 3. So let's take a look at this one. Here is a good tip. This is a good tip for the day here. When all of these signs are a sum, this is a theorem you'll learn next year, but it's an easy one to remember, and it's a good tip, so I want to tell you now. If all of these are sums, then that means there are no positive roots. That is very useful. And you'll learn why later next year. But keep this in mind, if everything is a sum in your polynomial, you don't have to test any of the positive roots. So that takes us right to the negatives. Our possible roots are the factors of 36. Okay, so if I try (1), that if I'm just going to plug it in, that would give me -5 plus 7 minus 15 plus 36. That's not going to give me 0. So (1) is out. Let's try division by (2). Let's see what happens here. So I have 1, 5, 7, 15, 36. Let's see, I just want to double check. Okay, we're good. So bring down the 1, (2), 3, (6), 1, (2). I'm not going to get 36, right? So I'm done with that. Let's try (3). 1, 5, 7. And this is why it's important that you have really good synthetic division skills, right? Hopefully you're getting faster at it because you're going to be doing a lot of them. (6), 1, (3). Oop, there's 1, right? 36, (36) gives me 0. Okay, that is a negative there. Kind of blended in with the 3. Okay, that's good. Now, here's another thing I want to keep in mind. Another important tip for today is that you can have those repeated zeros, right? So if negative 3 works, or now we're just down to a cube because we started with the 4th degree, negative 3 could be a 0 again. So let's try it. So negative 3, negative 1, 3, 4, and it did work. So there you go. Of course, that's not always going to happen, but you don't want to just move on to the next one, because then I'd be testing all those other negative factors of 36, and I wouldn't find this, right? So when you find a factor that works and you're not down to a quadratic yet, or find a 0 that works and you're not down to a quadratic yet, try that number again. Always remember that, okay? So you can have repeated zeros. Ooh, what's going on with my pen here? Okay, keep that in mind. So that means, because negative 3 worked twice, that we would have a factor. If we put this in factored form, it would be x minus 3 squared, which again means at x equal to 3, there would be a what? A turning point, right? We'd have that turning point on the graph, and you could check that out again by entering this into Desmos. Okay, so we're almost there. Now we've got our quadratic. X squared minus x plus 4. From quadratic formula, I get negative b is a positive 1 plus or minus b squared minus 4ac all over 2a. So that's positive 1 plus or minus, that's negative 15. So I'm going to bring out an I, root 15. There's nothing I can do with that root 15, so it just stays that way. So here's my solutions. 1 plus or minus I root 15 over 2 and negative 3. And we don't write it twice, even though it's a repeated 0. We still just write it once. Okay, let me check that against my key here. There we go. Okay, so one more theorem for today. The conjugate root theorems. So let P be a polynomial function with rational coefficients and let A and B be real numbers. Then if A plus B, or A plus root B is a root, then A minus root B is also a root. So remember, these are conjugates, just like A plus B, A minus B. Right? The only difference is these are root B and negative root B. So they have to occur in conjugate pairs when you have rational coefficients. Okay, so what that's saying is, say for instance, if I did have A plus B, say I didn't have conjugates and I had the A minus root B. Do you see how when I multiply this out, at some point I'd have that minus A root B, and nothing's going to make that cancel out, so I wouldn't have a rational coefficient. Okay, so that's why they have to occur in pairs, because you'll see when we multiply these pairs, then the irrational part will drop out. It's the same thing for imaginaries. When I have a root of A plus BI, if I have real coefficients, then I also have to have A minus BI as a root to give those real coefficients when we multiply out the factors. So let's try an example and you'll see what I'm talking about. Let's see. So we have a quadratic function with rational coefficients in standard form, and 2 plus 5i is a root. So when I see that has rational coefficients, then I also know that 2 minus 5i is also a root. Okay, it has to be that way to have those rational coefficients. So let's take a look at how we would multiply these out. So remember, when you have a number like 3 is a factor. If 3 is a factor, then, if you have 3 as a root, then x minus 3 is a factor, right? So it's always x minus It's always x minus your root, right, that gives you the factor. So let's actually go over here where there's more space. So in this case, if this is my root, that means I have x minus 2 plus 5i. Okay, that's one factor. The second factor is x minus 2 minus 5i. So when I distribute that negative, I get x minus 2 minus 5i and x minus 2 plus 5i. Now, you could do the distributive property 3 times. That would certainly work. Distribute the x, distribute the negative 2, distribute the negative 5, because we do have to multiply this out. I'm going to show you a nice little shortcut. If you group these two terms together and treat them as a single term, do you see how this would be in the form of a minus b, where the a is the x minus 2 and the b is the 5i. That would make this a plus b. So we can follow our pattern for doing a minus b times a plus b, which remember is a squared minus b squared. So I'm going to take my a, which is x minus 2, I'm going to square that, and then minus the b part is 5i, and I'm going to square that. It makes it a lot simpler once you get used to this pattern, and you should be used to this pattern. We've been focusing on this in the last several sections. You should be able to multiply this out much faster than distributing 3 times. But you can always go back to that idea as well. I'm just going to do it this way. So we have x squared minus, remember middle term is 2 times 2 times x, so it's minus 4x plus 4. And then minus, that's 25i squared. And what does I squared equal? Hopefully you said negative 1, which makes this a plus 25. And then I add that to the 4, and I'm done. X squared minus 4x plus 29. So do you see how much faster that is than doing all of that distributing? Right? This is a much faster process. You have to understand what we're doing here. So certainly ask questions about this in class if you have any. We're going to do one more. Let's look at letter B. Now this one, we have irrational roots and imaginary. Okay, we're going to have both. So it's degree 4, rational coefficients. So when I see that word rational and I know it's degree 4, I know I need 4 roots, and I know from the fact that it's rational that the conjugates have to be roots as well. So this tells me that 3 plus root 7 is a 0, and if 4i is a solution, the conjugate of 4i is negative 4i. Right? Remember, they have that form a plus bi. In this case, a is 0, so the conjugate of positive bi is negative bi. So if you have a pure imaginary, that's what we call a pure imaginary because there's no real part, then the opposite of that pure imaginary is its conjugate. So let's set up our factors. So from the first given root, we have x minus 3 minus root 7. And then from the conjugate, I would have x minus 3 plus root 7. From the imaginaries, I have x minus 4i and x minus negative 4i, which is plus 4i. Okay, let's take away the parentheses. Again, see how we have the conjugates. This time a is x minus 3, and b is going to be the root 7. So when I multiply these, so notice I have the plus and the minus, I'm going to have x minus 3, quantity squared, plus the square root of 7 squared. So when I square this, I get minus 6x plus 9. Oh, I made this parentheses there. And then the square root of 7 squared is just plus 7. So I get x squared minus 6x plus 16. From these, when I multiply the factors with the imaginary roots, I get x squared minus 16i squared. Remember, that becomes plus 16, so it's x squared plus 16. Okay, now I have to multiply these two together and I'm done. So I'm going to bring this one up here and I'm going to start distributing. Okay, x squared times x squared gives me x to the 4th. I'm going to keep distributing that x squared, so minus 6x cubed plus 16x squared. Then I'm going to distribute the 16, so I have plus 16x squared minus, that's 96x, and then plus 16 times 16. Oh, wait a minute, something's not right here. Oh, shoot. Let's go back to here for a second. When I did this, that should have been a minus. Darn. Hopefully you saw that and we're wishing you could say something to me, but at least I caught it. Okay, so that changes that whole thing to 2. That's a little better. I knew something just didn't seem quite right there. Okay, so let's go back, make this a 2. So that makes this a 2. When I distributed the x squared, okay, so let me just check. Minus 6x cubed plus 2x squared. Okay, that looks better. Okay, so now we have minus 16x squared minus 96x and then plus 32. Okay, we add up all these terms. We should get that, and we do. Okay, good. So it's quite a bit of work, and that's why, again, these skills from the past are so important. I really hope you try learning this shortcut that I'm showing you here. Just make sure you put a minus there, not a plus. But this is a really nice shortcut. You could distribute 3 times, right? Multiply everything by x, multiply everything by -3, multiply everything by root 7, just like we did over here, right? You could distribute that way and get this expression as well, but it's going to be a lot more work. So please try to learn this shortcut. It's a good one. Okay, so for our concept summary, we talked about the rational root theorem, right? Which, remember, that's that P over Q, where P is the factors of the constant, Q are the factors of the leading coefficient. So when we set up that ratio, remember, it can be positive or negative. We get all of the possibilities, okay, that can, of the numbers that can be possible roots for that polynomial. The fundamental theorem of algebra tells us that if we know the degree of the polynomial, then we know we have that many solutions. So if the degree is 5, we've got 5 solutions. If we've got degree 4, we've got 4 solutions, and so on. And then the conjugate root theorems, so just remember they have to occur in conjugate pairs when you have real coefficients. So if a plus root b is a root, then a minus root b is a root. For complex conjugates, if we have real coefficients, if a plus bi is a root, then a minus bi is also a root. So that concludes this lesson. This was the entire lesson. Okay, we did it all in one shot this time so that we can have a little extra review time the second part of the week. So I hope you enjoyed the lesson. Come ready to ask questions. I know this was a tough section, but come ready to ask questions, and I'll see you in class. Have a good day.